Hey everybody, welcome to video notes for topic 7.7, acid rain. We're starting out on page 418 here, reviewing the sources of air pollution that contribute to acid rain. So it is formed as a result of the primary pollutants NOx and SO2. These pollutants transform in the presence of oxygen and water in the atmosphere to become the secondary pollutants, sulfuric acid and nitric acid. We'll go through that process here in depth. The first thing to know, though, is that coal-burning power plants are the #1 anthropogenic source of sulfur dioxide, SO2. They also release NOx, but the primary source of NOx emissions is vehicle exhaust. So this could be cars, buses, anything that combusts a fossil fuel for its fuel source. So limiting acid rain is accomplished primarily by targeting reductions in these key sources of SO2 and NOx. A piece of legislation you'll remember from the beginning of this unit, the Clean Air Act, sets emission standards for vehicles and power plants, and as a result it's been really effective at reducing NOx and SO2 levels in the atmosphere and therefore reducing acid rain. So acid rain over the years has become a much less pervasive issue than it has been because of the Clean Air Act. So it's been a successful attempt at reducing those source pollutants that lead to acid rain formation. Now we'll talk about the actual chemical formation of acid rain using this little diagram here. So again, as a review, it starts with NOx and sulfur dioxide emissions. These are the primary pollutants. So these come directly from the combustion of fossil fuels, especially in coal-fired power plants for sulfur dioxide, and vehicle emissions for NOx. When they get into the atmosphere, in the presence of oxygen and water, they transform into the secondary pollutants, nitric acid and sulfuric acid. You don't have to memorize the chemical formulas for nitric acid and sulfuric acid, but it can be helpful to know them. HNO3 for nitric acid, H2SO4 for sulfuric acid, because it can remind you that we need to add something to NOx and to SO2 in the process to turn them into secondary pollutants. And if you look at what's changed about their chemical formulas, we've added hydrogen and we've added oxygen. And so that can help you remember we need water in the atmosphere, H2O, and oxygen in the atmosphere, O2. So again, this is kind of the definition of what actually produces a primary, or a secondary pollutant, I should say. It's a primary pollutant that undergoes transformation in the atmosphere to become a secondary pollutant. So acid rain coming from nitric acid and sulfuric acid is a prime example of a secondary pollutant. We're not quite to acid rain yet, though. There's a second step, and it's called dissociation. So in dissociation, these compounds, nitric acid and sulfuric acid, dissociate, or they break apart into two separate ions. Remember, ions are compounds that have a charge to them. So we will see nitric acid, I switched these around, nitric acid will dissociate into nitrate, NO3-, and an H+, or a hydrogen ion. And sulfuric acid will dissociate into two hydrogen ions, two H+ ions, and a sulfate ion, SO4, with a -2 charge. This happens in the presence of water. These compounds dissociate into these two separate ions. Now in the formation of rain, these hydrogen ions, H+ ions, actually get trapped into water droplets and they fall down into aquatic habitats or into soil, terrestrial habitats, and those can lead to the effects that we're going to talk about shortly. But just as a reminder, I've circled these two H+ ions in red because this is the key to acid rain. These hydrogen ions that dissociate from nitric acid and sulfuric acid get trapped into water droplets and falling down into aquatic or terrestrial habitats. That's how we actually get a decrease in the pH or an increase in the acidity of these habitats. So now we'll talk about what those environmental effects are. So we have three big environmental effects of acid rain that we need to know about. The first one is that we can have a decrease in the pH, so we lower the pH or we make it more acidic in aquatic habitats or water sources. And this is a problem because many aquatic species, such as fish and amphibians, especially have narrow pH tolerance ranges. So remember, species all have tolerance ranges for all sorts of conditions, and pH is a really vital condition or really vital attribute of a habitat for which these organisms have a tolerance range. Many aquatic organisms have pH preferences or tolerance ranges in between 6.5 and 7 or 7.5. So when the pH decreases outside of their range of tolerance, in this case it's moving below their range of tolerance, they can experience reproductive or developmental delay. So especially when we get down into the 5.5 to 6 range, many amphibians have developmental or reproductive delay or difficulty. And then they can even die if the pH becomes too low. So for example, below a pH of 5, many amphibian species cannot survive, especially species of salamanders. They have really absorbent skin and are especially prone to decreasing pH in their water sources. This can decrease biodiversity, which can disrupt food webs. So remember, we call this a trophic cascade. That's where a large decrease in one species or their removal entirely can affect both their predators and their prey, or even species they compete with or ones that they have symbiotic relationships with. Acidity or lowered pH can also make metal ions more soluble or easily dissolved into soil or water. And so two examples of this are aluminum and mercury. These are metals that are found naturally in many rocks and soils, but they are toxic to many species of plants and animals. So those can also have an impact on biodiversity. They can inhibit the growth of plants by damaging their roots, or they can actually kill plants or terrestrial or aquatic species if they become too soluble or too present. And then finally we have the loss of nutrients in acidic or lowered pH soils. So if the pH in a soil becomes too acidic, becomes too low, that leaches away or displaces positively charged plant nutrients from the soil. So some examples of this would be magnesium, calcium, potassium, sodium. These are all nutrients that plants need, and because they exist in positively charged ions, H+ ions being added to the soil leaches them away. It actually bumps them out of their binding sites on clay, and they can be drained out of the soil by water. This can also trigger some food web disruptions, especially if these plants that depend on these nutrients are either shelter or food sources for other species. And then finally we have human health effects of acid rain. So it's important to know acid rain does not really directly have human health effects. So like if your skin comes into contact with acidic rain, your skin is a fine barrier to that. It's not going to be harmed by acid rain directly. The precursors, NOx and SO2, do have human health impacts, the respiratory irritants, but the threat to humanity from acid rain from a direct standpoint is more to the corrosion or the breakdown of buildings and structures, or buildings and statues, especially ones with limestone and marble. This is because the H+ ions react with calcium carbonate, gives off calcium ions, but it actually breaks down the structures in the process.